Welcome to the fifth video in this series. The topic this time is quantum electrodynamics and the standard model. I believe this is one of the most interesting video in this series, since we will get to the theory of what we think of physics in 2021. And in order to get there, we will start with electrodynamics. We will discuss the Lagrangian of EM, and then we will discuss the theory of fermions, and that leads to the Dirac equation, and then the Dirac Lagrangian. After we have done that, we will put these two things together and create the Lagrangian of QED, or quantum electrodynamics, which is one of the mostly tested theory in physics. And all of these tests are all successful, so we can also say this is one of the most successful theories in physics. In the end, we will make some categorizations by different spins, and we will input the missing piece, which will be the vector bosons in the standard model. So by the end of the video, we will have a picture of what is the mathematical formulation of the standard model. Until so far, we haven't really included any interaction between these fields, and actually, so we had a kind of boring universe when things were just going freely without any interaction with other particles. So let's now complicate things a bit and include certain interactions. And so let's just start with the electromagnetic field. So we could say that 5.1 is going to be electrodynamics. So electrodynamics is essentially electromagnetism when things change. And so we will use the four-vector notion to denote the electromagnetic field as one thing. So we are going to call this A, and it's a four-vector, so there is a mu index, and it depends on where we are. So this is the so-called vector potential. So the vector potential is understood as I said, it's a four-vector, so it's going to have four components. The first, or the zeros component, is the electromagnetic potential, which is scaled with the speed of light. And the rest is the vector potential, as we met it in the past. So the Vx here is the scalar potential, and the Ax is a vector, a three-vector. That is the vector potential, magnetic vector potential. So this was you could say this is the electric potential here, and this is the magnetic vector potential. Which is defined by the fact that we can get B by taking the rotation or the curl of this A vector, and the B was vector 2. So this was the same as the nabla cross A. So in order to have this in a relativistic form, we will introduce a tensor, which is called F mu nu, denoted with F mu nu. So F mu nu is an antisymmetric tensor, and it's defined as the derivative of the A, the nu's component of the A4 vector derived by the mu component minus, it's an antisymmetric tensor, so we just swap the indexes. So that's why we have two indexes. There is no repeating index, so there is no summation here. And we want to figure out the Lagrangian of the electric field. We need to create something which is a scalar. Lorentz scalar. So we need to have these indexes gone, and I was mentioning that right now there is no summation, so this is just a tensor. So what we could do is that when we are when looking for a scalar, we could try to have f mu nu with f mu nu. So now finally we have repeated indexes, and so that will lead to a scalar. And that scalar is essentially, if you do the calculation, it's going to be 2 times b squared, which is a vector. I mean, when you do the b squaring, it's not a vector anymore, but b was a vector originally, minus b squared. So it's the square of the magnetic field minus the square of the electric field. So if we define the Lagrange density like this, then so this is a scalar first of all. So we could try to use this as for our Lagrange density, and so actually we need to include a factor which is going to be explained later. You know, that again, this is a convenience factor of minus 1/4, and then we still have the same thing, f mu nu f mu nu. So this is the simplest Lagrangian for electromagnetism. And actually, if we use this Lagrangian and go through all the methods that we learned in the past, the outcome of this is going to be the Maxwell equation. So as we have seen in the past, the big deal is to find the Lagrangian, which needs to be a scalar. So then when we had this antisymmetric tensor, and we just look for the simplest thing to make that into a scalar, we find the Lagrangian that leads to the Maxwell equation. Let's now put a spin into these particles. So this is going to be described 5.2 of the Dirac equation. So when Dirac was trying to figure out the theory of the quantum version of electromagnetism, he actually was looking for a first order differential equation. And the issue with the Klein-Gordon equation was that it was a second order thing. So what he was doing is that he tried to move from the Klein-Gordon equation into a first order one. And so if you look at the Klein-Gordon equation, we had the derivative twice plus n squared. So that has the form of a squared plus b squared. This is something which we used in the past as well, that we have an identity using complex numbers that could lead to this kind of situation. And that would mean that we have the square root of these things. So, well, whatever that means for now, let's just take the square root of the derivative operator, and then we have the square root of m squared, so that's just an m. And as we discussed, that the identity includes a complex number here. So again, we have the square root of the square of the derivative and minus I m. So as you could see, this is really a weird situation because we don't know what does it mean to take the square root of a partial differential operator, right? So this is a square root of a partial differential operator. So Dirac's method of doing this was to define a new 4-vector called gamma mu. So gamma mu is a new 4-vector, and he just defined that so that what we're looking for is going to be solved. So he said that gamma mu times the differential operator d mu times gamma mu of the differential operator with the mu parameter is the same as the d mu d mu. And if this is true, then we know what is the square root of this differential operator. So to make this true, that means that when you take the zeros component of the gamma and take the square of that, that's going to be 1. When you take the first component of the gamma and take the square of that, that's minus 1. And then you do the second component of the gamma and take the square, that's also minus 1. And when you take the third component of the gamma and square it, that's also minus 1. And there is also an anti-commutation relation. So if mu and nu are not the same, then we define this anti-commutator, which is now this kind of bracket. So gamma nu in this bracket means, like with the commutator, we had the multiplication of this minus the other way around. And so now what we are going to do is the multiplication of these, but we don't subtract, but we sum gamma nu. And this has to be 0. That this all of these things just come from the definition of this 4 vector. So to put all this together, what we get is that this gamma nu, taking the anticommutator of these two, we get 2 times g mu nu. And I hope you remember what this g mu nu was. This was the metric tensor, and you actually kind of realize this 1 minus 1 minus 1 minus 1 signature inside of the metric tensor. So interestingly, when he tried, he first thought that these would be numbers. And the thing is that you cannot make this true using numbers. And the only way to do that is that if these numbers are matrices, 4 by 4 matrices. So the only way is by 4 by 4 matrices. But actually, there is no unique way of writing these gamma matrices. There are different ways of doing it. And so there are these we call different representations. And when you use the Dirac representation, that's very convenient for the non-relativistic approximation. And the other widely used representation is by Weil. So that's what also called chiral representation. That's very convenient if the energy is much, much higher than the mass of the particle. So that's the so-called ultra-relativistic regime. So let's first go into the Dirac. So that's the Dirac's representation of these gamma matrices. So this is used usually when you have that the energy is very low. So this is the non-relativistic version. So in the Dirac representation, gamma 0 is the identity matrix here, 0, 0 minus the identity matrix here. So I mentioned that it's a 4 by 4 matrix. So this means that this identity matrix here is actually is the 1, 0, 0, 1 matrix. And we also sometimes denote the identity matrix as 1 like this. I could actually have this notion. And the rest, which I'm going to denote with I, if you remember, we were always using the Greek when we count from 0 and the Latin letters when we count from 1. So this I is going from 1 to 3, and that's going to be the 0 and the sigma Pauli matrices sigma I minus sigma I and 0 here. And before I actually mention what the sigma matrices are, let me tell you what is the Weil representation. So Weil, also called the chiral, and it is used when the energy is much bigger than mc squared. So in the Weil representation, the gamma 0 is 0 identity matrix here, and 0, and the rest from I is the same as 0 sigma I minus sigma I and 0. So that's actually the same as in the Dirac representation. And then we could say that what we used to, let's say, that the Pauli matrices are the sigmas, sigma I. So those are defined sigma 1 is the same as 0, 1, 1, 0. Sigma 2 is the same as 0, minus I, 0. And sigma 3 is the same as 1, 0, 0, minus 1. So what's common in these is that the determinant is 1 and the trace, so the sum of the diagonal element is 0, right? So the sum of diagonal is 0 and the determinant is 1, right? Because 0 plus 0 is 0, 0 plus 0 is 0, 1 minus 1 is 0, and then you do the determinant. 0 times 0 is 0, plus 1 times 1 is 1, and then again minus I times I is 1, and 1 times minus 1 is minus 1. So the absolute value of the determinant is 1. So we could think about this, that we have a vector of these matrices. So sigma vector is a vector of matrices. You remember that we really just think about vectors as a collection of information. So if all of this is true, then we can go back and insert this information that we had gamma mu del mu plus I, the complex I, times the mass, and multiplied gamma nu d nu minus the IM acting on the psi is 0. So this is still the Klein-Gordon equation, right? This is the Klein-Gordon equation. And we wanted to take the square root of this, which now seems to be simple, or like we could say that if we want to solve this equation, well, we can do that by saying that one or the other is 0. So let's just say that the solution to this is that the gamma mu, the mu plus the Im acting on the psi is 0. And this is the Dirac equation. So you could ask what the psi is now. So the psi has 4 components, and it's called a Dirac B-spinor. So psi has a Dirac B-spinor, has 4 components. If we would like to multiply it with I, we can do that. So that's another form that I comma mu del mu minus m is the acting on the psi. The 0 is a different is another form of the Dirac equation. Let's actually introduce one more notional difference, or one more notion that will make things look a bit nicer. That is the slash symbol introduced by Feynman. Feynman slash notion. The slash symbol is this. So I have some letter which I'm slashing. It's the shorthand notion for the gamma mu a mu. So if we want to use this notion for the Dirac equation, I can go back to the red again. That means that the Dirac equation is I times the del, and I make the slash of it. So like I'm contracting two indices, so that's not going to be a vector anymore. So that there is no vector notion anymore. So del slashed minus m acting on this psi bispinor is 0, is the mostly known form of the Dirac equation. We could also take the Hermitian conjugate of this equation and get that the dagger of the psi and the zeros component of the gamma matrix multiplied with minus I del slashed minus m, the mass, is the same as the dagger gamma 0 I del plus m, and all of these are given. So please note that in this case, the partial operator acts to the left. And with this, we could define the so-called adjoint bispinor, adjoint bispinor, by taking these two things together. The notion is a bar on the top of our psi. So psi bar is the same as the psi dagger and the gamma 0. So with this, we can put this back and get that the psi bar I del slashed plus m is also the same as 0. Okay, so now let's look at the solutions to this equation. So the solutions to the Dirac equation. Let's first realize that the gamma mu I del mu is actually the same as the P operator, the momentum operator slashed. So we are doing a summation here because we have two indexes. So let's just what this is something which we did in the past too, to factor out the zeros component. That's going to be that the gamma 0, the P0, it's an operator, minus the rest of the gamma matrices, which is the rest of the vector of the gamma matrices. So I could do this. The P, this is the spatial part of the momentum, the form momentum, and we have minus M acting on the psi. So I am writing the Dirac equation out in a form where the time component and the space component are separated. And now let's remember that the gamma matrices have this two block shape. And so based on this, we could divide the bispinor into two parts, into two spinors. So that's why it's actually called a bispinor. So the psi could be written as two spinors, psi something, which we will now call L, and psi r. This stands for left and right, and that's going to be something that will come up in a second, why these are called left and right. So each of these have two components. So psi L and psi R have two components. They are spinors. So we could rewrite the Dirac equation just by this thing. So you remember what was the gamma 0? That was the 0, 1, 1, 0 operator. So when we act on that with the P0, we will get a 0 here, a P0 here, a P0 here, and a 0 here. So this was this term. And now, when we include the Pauli matrices and multiply that with the vector of the spatial part of the before momentum, we get minus 0, the sigma vector as the P vector, minus the sigma vector and the P, three vector part of the P, and the 0 here. And we have this M is multiplied with 1, so that's going to be the usual 1, 0, 0, 1 operator multiplied with M, so we do M0, 0, M here. So this is exactly the same as this thing, right? So this was this part was this part, and this part is this part. So this is acting on psi and results to 0. So now, because we have this block structure, well, I could actually also write that that this psi was now the same as psi left, psi right. So doing the matrix vector calculation here, this leads to two equations. We have P0 minus the sigma vector p vector acting on the psi r, and then we also have a minus m times the psi l. So I'm just going to put this into the other side. So this equals to m times psi l. And when we do the other row of the matrix vector multiplication, we get again p0 vector plus sigma vector with the p vector acting on the psi l, and that will equal to m times the psi r. And if we take the special case, if we are in the massless case, so if m is 0, that leads to p0 minus sigma p acting on the CR 0, and also that the p0 plus the sigma p acting on the psi left is 0. So that implies that the four-component state splits into two-component states that seems to be not mixed by the equations of motion. That kind of means that there are two kind of massless Dirac particles, and one of them is called the left-handed, and the other is called the right-handed particle. So this leads to left-handed, right-handed. This is the right-handed, and this is the left-handed. And they don't really seem to be speaking to each other when they are massless. So if we have a massless particle, then the P0 is the same as the energy corresponding to that momentum. And that is, we said that this is C times P, but if we just take C to 1, this is going to be the absolute value of the momentum. So if I include this and rearrange a bit, then what we get is that sigma p vector divided by the absolute value of this vector p acting on the psi r is the same as psi r, and we also get that the sigma p vector divided with the absolute value of the vector p multiplied with the psi left is the same as minus the psi left. So these are now the equations of motion to solve. So these are the equations of motion. And we could turn back to the massive case. And so we will see that the left and right-handed wave functions are coupled into each other by the particle's mass. So we could think about a massive Dirac particle as an oscillation between the left and right-handed particles, and the rate is determined by the mass. So, okay. So the mass couples left and right. You could think about a particle, a massive particle, is like left-handed, right-handed, left-handed, right-handed, left-handed, right-handed, left-handed, right-handed. So left, right, left, right, left, right, left, right. It's an oscillation on massive Dirac particle is an oscillation between left and right, and the rate of this oscillation comes from the mass itself. So when we are looking for the insides of these two wave functions, let's see the solution of the Dirac equations in the form of UP. So form of solution to be U depends on the P and the exponential minus IPX should be the same as U left and the U right. So these both depend on the P. And we have the exponential form IPX. And let's also look for the second one as VP. So VP exponential with a plus sign now, IPX, is again has two components, V left and V right. This depends on P. And we again have the exponential with the plus sign of Px. Physical meaning is that this describes the particles and this describes the antiparticles. These U and V have to also satisfy the Dirac equation, which means that we could write, based on this, we could write that the P slash operator is the same minus M acting not on the psi now, but on the UP is 0, and also the minus P minus M acting on the V depending on the P is 0 as well. So let's have the special case when the particle is not moving. So that means that the momentum is 0. If momentum is 0, then the equation simplifies to, this is not here. We just have the M with the minus sign, and so that is going to be minus M, the M here, and the minus M here, acting on the U from this, and the plus is on here, acting on the UR. So this U, you remember, has left and right components as well. So this is 0. The solution to this is going to have the form of the square root of the mass and some vector, which I'm going to call the components xi and xi. And also the same thing for the V is going to be the square root of M, but let's call the components eta and eta. So this describes the matter, and this is the antimatter. So these xi and eta are spinors, and as the name suggests, these are connected to the spin. So connected to a spin. They can have two eigenstates, either, so psi1 is 1, 0. You could also think about it as the up spin, and then the psi2 is the 0, 1. That is the that is the down spin. For the particles, and then we have eta 0, 1 is the up spin for antiparticles, and we have the eta 2, which is now, this is all the opposite of what we saw for the particles. So we see that while the 1, 0 was the up for the particles, the 0, 1 is the up for the antiparticles, and the other way around with the down spin. So if we want to move that we are not anymore at the rest frame, then these u and p's will move into the following. The u, depending on the p, describing the spin with the letter s. So ups is the same as the p sigma under the square root, and the psi s is the first component, the first two components essentially, and the p sigma with the psi s is the third and fourth component, and the v, which again is now something which describes the spin and depends on the momentum, is going to be the p sigma under the square root and the eta s, and we have minus the p sigma under the square root of the eta s. So these are now the four component vectors which have two components. These are called spinors. So these are essentially p-spinors, and I actually missed that there is a bar here and here. So these are understood as now the four vectors. So the sigma is the 4 vector where the zero component is the identity matrix, and the rest is the sigma, while the sigma bar is the same, just with a minus sign, with a minus sigma here. So S was for the spin, and it can have values of 1 or 2, and that are these vectors here. The next step we would need to figure out is some normalization factor, which we will now just put here. After that, we are able to express an arbitrary particle that is a solution of the Dirac equation. So it is a particle that has a spin. It is going to be an integral over the momentum space and a sum for the spin states. So the final solution then, final solution, that the psi wave function or the field for a particle that is a Dirac particle at an x spacetime is the same as the integral of the dp cubed 2 pi on the third half power 1/2 2 EP on the 1/2 power. So this is the normalization factor which we denoted earlier with the gamma, and we have a sum for the spin s, which goes from 1 to 2. We have some coefficient a corresponding to a given momentum and a given spin, and we have this u part of the equation that is different for different spins, and it depends on the momentum, and we have this exponential of ipx. So this is the field describing a particle, a Dirac particle. And we can also discuss that what is the antiparticle. So antiparticle, depending on x, we have the same normalization and integral for the momentum space. We have the 2 pi 3 over 2 power 1 over 2 t EP 1/2, and the sum for the spin 1 to 2, and it's going to have a different factor here. It's going to, let's just call it p, and it's also different for different spins and different momentums, and it's actually the complex conjugate of this number, and we have the solution v, which again is different for each spin, and it depends on the momentum, and the other change is that we make this into a plus sign. So if we want to describe the Dirac field as a whole, then Dirac field is going to be the sum of these particles and antiparticles. So psi x is the same as the integral dp cubed 2 pi 3 over 2 1 over 2 EP under the square root, and the sum for the spin from 1 to 2 of the ASP, which goes together with the US, again it's a function of the P, exponential with the minus sign, plus the B star for different spins and momentum, V depending on the P, different spins, and the exponential is with the plus sign IPX. So this is really the solution to the Dirac equation leading to the Dirac field. It is the one which describes particles with a spin. One more thing that we could note here is that this EP is the relativistic energy. So what we do is that we take the p squared plus the m squared, and we take the square root of that. Of course, c was set to 1, h bar was set to 1 in this whole derivation. Let's now jump into QED finally. So 5.3 is QED. So what did we do so far? 5.1 was about the electromagnetic field, and 5.2 was about spinors. So particles with spin. And what we need now is that we need to do the quantum mechanical version of QM of these two things, of 5.1 and 5.2. We learned in the previous video the quantization method that is called the canonical quantization. Canonical quantization. So canonical quantization machine. So the first step is to figure out the Lagrangian. So we already know the Lagrangian for the electromagnetism. That was this minus 1 over 4 F mu nu, F mu nu. So we need to figure out what is the Lagrangian for the Dirac. We follow a similar strategy that the Lagrangian has to be a scalar. And so we had this Dirac equation of I del mu del slash minus m acting on the psi. So this was not yet um, a scalar. So the way that we can make a scalar out of it is to multiply with the adjoint spinor. So now if we add these two together, then and we plug it into the Euler-Lagrange equations, the solution to this psi, which is now an operator, psi x is going to be the integral of dp cubed over 2 pi on the third half power 1 over the 2 EP on the square root of the sum for the spin 1 to 2 of the creation operators now, SP operator, US depends on the P, exponential of minus IPX plus B SP operator, which is now, which is starred in the past, now that it is an operator, it's a dagger, or joint. V, depending on the S, and the P, and the exponential is with a plus sign. So this is very similar to what we have seen earlier. The only difference is the hats. So like earlier, but A became a operator, B hat, and B became B hat, which B star became B dagger hat. So earlier, these were just some coefficients, and now we learn that these are the creation and annihilation operators. So this Dirac equation led to this, or Dirac Lagrangian led to this solution. And these were the creation and annihilation operators. So the next step is to merge these two, right? Before we do that, let me actually introduce some parts of the gauge theory. So gauge theory. Gauge theory is a theory if the Lagrangian of the theory is invariant under certain transformation. So the Lagrangian is the same as the Lagrangian after a transformation. So Lagrangian prime is transformed Lagrangian. So we could say say an example, the magnetic field is calculated from the A vector potential as the curl of it. However, if I change A to some full gradient of a function, so if A becomes this A plus thing, then what is going to be the root of A is going to be the same as the curl of the A plus the gradient of this F. So, the A is changed, but the B is not. We have certain freedom in changing the vector potential. This really means that the choice of the vector potential is not unique. A is not unique. To deal with this situation, we will introduce the so-called covariant derivative. Covariant derivative. And we call that, or denote that with an uppercase D. So that's going to be defined as our standard derivative d mu, and we add to this I, some factor q, and the a mu. A mu is the pole vector potential, and the q is the coupling constant of the interaction. If you want to give an example, then this coupling constant of the interaction for Em is the charge. And that's why it kind of makes sense to call it Q, but we also call it anything else, right? It doesn't really matter. So with this, we can finally write down the Lagrangian of QED, the Lagrangian of QED. This is the merger of these two things. So we had 1/4 F mu mu F mu mu. This was the electromagnetism part. And now we have the Dirac part, which was the adjoint B spinor. And now that we introduce this covariant derivative, let's use that instead of the derivative from earlier. So I uppercase D slash minus M acting on the psi is going to be the Lagrangian of QED, where the d mu was just the gamma mu, the d slash was the gamma mu d mu covariant derivative defined above. Now going to what else is there in the standard model. So 5.4 is the standard model. So first of all, let me say that the QED Lagrangian was a huge success. It includes contributions from gauge fields and locally invariant Dirac field describes the fermions and their interaction. So mathematically, there isn't really too much new to the standard model. The standard model contains particles of spin 0, spin 1/2, and spin 1. So we have spin equals 0, 1/2, and 1. That's just it for the standard model. If the spin is 0, we call that a scalar particle. And the example for that is the Higgs boson. And actually, this is the only scalar particle in the standard model. We described this in the second section of the last video. And so this is described by phi, and of course an operator. The phi x was the normalization and the integration factor, integration measure of the 2 pi 3/2 1/2 energy corresponding to that momentum squared, and we had the creating operators with a given momentum and then transformed into Fourier transformed into the space from the momentum space into the space, and the annihilation operators which destroy particles with a given momentum, and the exponential was this IPX with the plus sign. So this is the field that describes the Higgs, and it is responsible, the Higgs is responsible for giving mass to the elementary particles. So the Higgs interactions give mass to elementary particles using the BEH mechanism. Broad angles and Higgs. So if the spin is 1/2, then these are going to be the fermions. Or the spinors. And so we have 6 of them. We have the up quark, the down quark, the charm quark, the strange quark, the top and the bottom quark. These are very similar. The mass increases as you go to the right. They are also packaged together like this: the U and the D, and the C and the S, and the T and the B. So these are the quarks. And we also have leptons. We have the electron, and to the electron we have a neutrino, the electron neutrino. We have the muon, and to that we have a neutrino, mu. And we have the tau particle, and to that we have the tau neutrino. And to all of these, we also have, of course, the antifermions. So that's everything which you see here, just with a bar. So U, T, C, S, T, B, bar, electron, neutrino, muon, neutrino, tau neutrino, and then bar. So these particles are described by the Dirac field, which we just discussed a bit ago. So the Dirac field was described with the psi. It's an operator, so we have a hat on it. We have the x. We have the integration measure for the dp cube over 2 pi 3 over 1 3 halves 1 over the 2 ep, and that is square root, and we have the sum for s equals 1 to 2 of the creation operator of particles and antiparticles u s p a minus e bx plus the b s p Dagger operator, and that goes with the vp for every spin, and the exponential is with a plus sign. This is what we just discussed. So the only thing which we have not discussed yet is the so-called vector particles. So if the spin is 1, this is called a vector particle, and what we have in the standard model is the photons. We have the W plus minus particle, the Z boson, and the glucose. So these are essentially responsible for the interactions. The photon mediates the electromagnetic force. The Z and the V are responsible for the weak force, and the gluons are responsible for the strong force. These forces are mediated by these bosons. We will discuss how to handle these interactions in the next chapter. For now, we just code the field operators with the vector bosons. So now the letter is going to be the A, and it's again an operator, and it's actually now a vector. So that means that it will have an index. So a mu at the x is the same as having the same integration measure. And now the summation will go for an index which we will call lambda. And so the lambda is now again included in the creating operators and annihilation operators. So we have the lambda and the p, that's unchanged. And what is now changed is that we introduce this epsilon, so-called polarization vector. So epsilon is again a lambda parameter. It has a vector index mu, and it depends on p, and has the same kind of IPX wave part as earlier. So we have again a lambda operator with a dagger, and there is also a p parameter here. And we have the epsilon star, epsilon mu star, which corresponds to each lambda. And we have this as a parameter of p, and now we have the exponential with the plus IPX. So that's the equation describing the bosons. So epsilon lambda mu p was the polarization vector. And we know about this that for massive particles, it obeys that the p mu epsilon lambda mu, which again depends on the p, is the same as 0. So this means there are 3 independent polarizations of a massive vector particle. That's the consequence of this, is that 3 independent polarizations. So that's why for the weak force, we have W plus, W minus, and Z particles. When we have massless case, then the gauge symmetry can be further exploited to eliminate one more polarization, which leads to 2 cases. So I should have said it here that for massive particles, we have this, and then this is an example. And then if you have massless, then the consequence of that is that we have 2 independent polarizations. And so we can have the example for that to be the gluon and the photon. So I mentioned the BEH mechanism. That's the only thing which is actually left from the standard model. So BEH mechanism, or also just sometimes called Higgs mechanism, which could be just this one thing, could be a whole university subject in itself. So here we just say that the mass of the fermions come from the coupling of the scalar field to the right and left-handed Dirac fields. We kind of mentioned this earlier, that the mass is the oscillation between left and right fields. So that means that the Lagrangian for the standard model will have to be proportional to this coupling of the bispinor, the adjoint bispinor with the left hand, and the adjoint, the normal bispinor of the right hand. And so the mass term comes from the interaction of these two with the phi Higgs field. So there are probably some factors in front of it, but it's going to be uh, it's going to be in the form like this, which is the which gives mass to the fermions. Mass of fermions comes from the interaction of the Higgs, comes from Higgs plus Dirac field interaction. And you can also see that it's the left-handed and the right-handed fields. Then we can also, we should have a term when the Higgs boson has a mass as well. We know it's a massive particle. So the Higgs should interact with itself. So that means that the Lagrangian of the standard model should be proportional to the Higgs interaction. So we will have to have terms in which we have the phi field and it's changing. So the change is going to be with the derivative, and we want the derivative to be covariant. So it's going to be the d mu, the d mu, and that's just a change in the Higgs field itself, and so it should interact with itself. So that we are denoting as the d mu, uppercase d mu phi dagger interacting, so multiplied with the d mu phi itself. So we can also say that this is something like the absolute value of the d mu on the field. Nice. This is the Higgs-Higgs interaction. So mass of Higgs itself. As we described in the second part of last video, we also have an interaction term. So which we denote with the V. So the Lagrange of this denominator will be also proportional to some potential for this Higgs field. We know that the Higgs field itself has a non-zero value. The vacuum itself has a non-zero energy, and the Higgs field has a non-zero energy. And so this V is described by the function of minus 1/2 mu squared phi squared plus 1/4 of some lambda phi to the 4. So these are not, the mu is not a 4 index, and the lambda is not a polarization. These are just constants for the potential. So mu, lambda are constants, not indexes or polarizations. And so actually this V looks like the so-called Mexican hat. So if you were to plot this, you would see something like this. And so this is the V phi. Phi was here. Okay, we should have interactions between the gauge particles. So that means that the Lagrangian of the standard model is also proportional to the term in which we have the F mu nu, F mu nu, as we discussed it earlier with the Maxwell theory. And this is the interaction of the gluons as well in Dirac of gauge particles. So we have the photon, the gluon. It's also customary to decouple the interaction between the fermions and the Dirac field itself. So we have a term where LSM is proportional to I, the B spinor, and the change in the spinor field with the slash. So altogether, we get the Lagrangian of the standard model. It's going to be a sum of these things. So Lagrangian of SM is the same, minus 1/4 F mu nu F mu nu plus I the bispinor, the adjoint bispinor, that's d slash the covariant derivatives slash plus d mu of phi self interaction of the Higgs squared plus the interaction between the left and right-handed fields, so psi left with the bar, and we have some matrices here, which we denote with a y, Higgs field interacting with the right-handed fields, and the other way around, that's we call HC, Hermitian conjugate, and we have minus potential of the phi. So the next thing to do is to figure out what this means, and that's for the next lecture. What to do with all these things. But anyway, we finally have reached the point that we can write down the Lagrangian of the universe as we know it as of 2021, and you probably have seen this Lagrangian in the media, like there are mugs showing this equation, there are t-shirts showing this equation. So I hope you feel a bit of satisfaction that you probably understand how we got here, not even if you didn't understand all the steps, you just have a feeling of what kind of terms there are in this Lagrangian and what they mean. Okay, now that we have the mathematical formulation of the SM, we can think about how to make all these abstract ideas into something measurable, right? The goal in physics is really to compare the theories with reality, and so we need to figure out how to transform all these abstract ideas into uh, into measurable things and compare it to reality. This includes the Feynman diagrams, and also you go into the details of what we do at CERN to research this. So it's going to be an exciting video as well. I hope to see you next week.